E-fields and electric potential for point charges. This is a review. This is not a tutorial or a sample solution problem, but just a review of what's going on in the basic concepts here. So I have this point in space, and around it I have two charges, a positive charge and a negative charge. And what I'd like to do is figure out what the direction of the E field, the direction and magnitude of the E field at this point in space. So to do that, I go to the definition of an electric field. An electric field is the path a positive particle would travel. So if I look at this point in space, and if I were to put a positive charge there, so this is my imaginary, massless, volumeless test charge. So let's say it's positive, and it goes right there, and I want to see what direction it's going to travel. So it's going to move in a combination from the two charges. The positive charge is going to repel it, so it's going to push it this way. So I'm going to call that charge number 1, and I'll call this charge number 2. So charge number 1 is going to move it that way, so that's going to be the direction of its E field. Charge number 2, they're oppositely charged, so it's going to attract it, and so I'll call that E2. So now what I need to do is add these two up. So when I add these two up, I'm going to get a solution triangle. Let's see, it's going to go over and down, or it can go down and over. That's the same thing. So let's say it goes over, and then it goes down. So add up my vectors, and then when I add my vectors, I want to make sure that I connect them tip to tail over here. And then my resultant vector is going to be here in blue. Okay, it starts at the tail and ends at the tip of the combination. And the angle I'm going to put here at the two tails for my resultant vector. All right, that's great. But now what I need to do before I can do anything with this triangle is I got to figure out the lengths of these sides. So to figure out the lengths of the sides, I'll go to my equations. And under the electric field is kq1 over r squared. So that's going to be kq charge 1 over the distance between the charge and this point in space. I'll call that r1. So that'll give me the magnitude of this charge that's going to the right. So whatever this is on the right, it's going to be kq1, over r1 squared. My 1 looks like an r, but it's supposed to be a 1. All right, now let's see. For the next charge, for E2, I'm going to do the same kind of calculation for E2. And I'm going to put it down here next to this arrow just to show what it's going to do. So E2 is equal to KQ2, that's the negative sign, negative charge, over R squared. Now when we're putting the charges in here, do not put the negative sign in, because negatives and positives, they're used to determine the direction. And we already did that when we said things were attracted or repelled. So we don't need to put anything there. So that's going to be E2. So these two equations will give me the length of these two arrows. Then what I'll do is I'll use Pythagorean's theorem to figure out what the blue arrow is going to be. And that's going to be the electric field. That's the magnitude. And the direction is going to be theta. And so I'm going to use tangent theta is equal to the length of the opposite side over the adjacent side in order to determine the angle in that corner of the triangle. In this particular drawing, that's going to be E2 over E1. All right, now what about the electric potential? So to figure out what the electric potential is going to be, that's going to be pretty easy. The electric potential, so that's going to be V, that's going to be KQ1 over R plus KQ2 over R. And that's R1 and R2, so those are the two distances. I should draw this down here as R2 so you can see it. And that's how you're going to figure out what the potential is. KQ1 over R, KQ1 over R, KQ2 over R. And I add them up. But this time, you got to make sure you keep the signs. So keep the signs. For electric field, ignore the signs and the math equation because you already used the signs to determine direction. But electric potential is a scalar, so it doesn't have direction to it, but it does have signs. So we have negative and positive electric potential, which means we have negative and positive energies. We haven't had that before, but now we do with electricity. So I keep the signs and then I just add them up. That's all I'm going to do to find the electric potential.